Hello everyone, I'm Sébastien Royer, a machine learning engineer, and today I will present to you one of my side projects, which is kind of edge AI and machine ops oriented app. It is the SkateSpotAdvisor. As some of you may know, I am also a skateboarder. And one of the problems I have with my skate friend is that we are never able to quickly decide where to have a session. We always end up checking a lot of things, like the weather, and the idea is to summarize the whole process into a single app and to use a deep learning model to guide us to make the best decision.
Okay guys, so this is a quick demonstration of my application. So first we need to fetch all the data and do all the inference for each skate spot. Okay, so here you can see we have a map. If I click on the markers, for example the Ansic marker, it shows a picture of the skate park. We have also here Préfontaine, beautiful skate park. As you can see, we have also cards. So we have cards for each skate park. And on this card, we have all the weather data and the traffic times, distance for where we are currently. And you have also the satisfaction score. So now it is the winter here. So the two skate parks which have good scores are the Spin and the Taz because they are indoor skate park, and all the skate park outdoor have score close to 0. I can also give feedback on the prediction if I click on thumbs up or thumbs down. I create a Google script, so if I click on thumbs up, it will add some data into the Excel sheet. And with this feedback, we follow the MLOps practice, and I can, after that, retrain the model to make better prediction.
Okay, so what is MLOps? The MLOps is a practice of streamlining the entire machine learning life cycle, from data preparation to the model deployment and monitoring. It brings together software engineering and data science to ensure models are reliable, scalable, and continuously improving in production. With MLOps, in company, teams can automate workflows to reduce deployment time and to deliver machine learning solutions that remain robust over time. To ensure full reproducibility across environments, I use Docker to containerize the entire workflow. I create two separate Docker containers, one dedicated to data acquisition and preprocessing, and the other for the model training, validation, and evaluation of the model. Since my model were developed with TensorFlow, I compared them with TensorFlow Lite to integrate them into my Flutter application. The Flutter app performs on-device inference, and user can provide feedback directly through the app. This feedback is then rejected into the dataset, allowing the system to continuously improve and naturally follow the MLOps lifecycle. The idea is to build a regression model. Our input or categorical index, for example, the weather. Where the index is 0, this represents a rainy condition. If the index is 3, it represents blue sky. We convert this index into meaningful vectors so the model can better capture the relationships and learn underlying patterns. The model then produces an output in the form of a score that represents the suitability of each skate spot. So for the first experiment, I fed the model all the available features, the weather condition, the temperature, the distance, and the traffic time, to see if it is possible to make a model converge. I show even through the training loss decrease and appears to stabilize, the variation loss oscillate heavily. This indicates a poor generalization and a clear overfit. So for the second model, I remove one of the features to test whenever the converge will improve, and we have the same issue, an overfit and a lack of generalization. So then I ask myself which input actually has the strongest impact? Does improving a full ranking-based score even make sense for a deep learning model? So I decided to simplify the problem by only providing two categorical inputs, the skatepark index and the river index. The river become a binary score, 0 if I will not go to the skatepark under those conditions, and 1 if it is a good option. It's important to remember that the finite choice of a skate spot also depends on the skater mood, which introduces a natural variability. So as you can see, after all the changes, the model finally generalized. Both of the training and the validation loss decrease together and stabilize around the same similar value, indicating that the model is now learning meaningful patterns instead of overfitting. I also use the cosine decay learning rate credit, which gradually decrease the learning rate over the epoch and help us improve the convergence. So this is the validation step. Inside the notebook, I also generate two cycles, one with a rainy river and one with a clear river. So for the left one, we have a bad river, so we will go into indoor skate park, and the model predict we will go to the Taz or the Spin, which are the two indoor skate park from Montreal, and all the outdoor skate park have a score close to 0. And with a clear river, we will go outside, maybe to a faraway skate park from Montreal. So we will go to Magog, we will go to Berthierville, for example, for L'Assomption, which are skate park more far away from the city. In this final part of the video, I will briefly present the Flutter software architecture. It is divided in 4 parts: the winglets, the screen, the services, and the model. The service layer handles all the inference processes, such as the inference, but also the acquisition of the river through an API, the geolocalization, and the distance calculation. So thanks for watching this video. You can connect with me on LinkedIn and leave a comment below.